All right, so in this video, we're going to be talking about similarity again. So if you remember, similarity was this concept of two shapes that were not congruent, but they had a certain pattern or a certain scale to them. And we talked about this with 2D shapes, and so now we're just going to apply it to a 3D shapes. But first off, again, a quick review on similarity versus congruency. So congruent shapes are shapes that have exactly the same angles, sides, pieces, everything. So all corresponding pieces are equal. Corresponding in this case is talking about like pieces that serve the same function, like height to height, length to length, width to width. Those are corresponding. So in congruent shapes, all corresponding pieces are equal. All the lengths are equal to all the lengths. All the height is one shape. It is equal to all the heights in the other shape. Everything's congruent. Everything's equal. And similar, the corresponding pieces aren't equal, but they share a common ratio or a common multiplier or divider to get from one to the other, and that's called a scale factor. So like maybe the heights in all one shapes are twice as much as the heights in all the second shape, or something like that. So they have a common multiplier or divider for all corresponding pieces. So one multiplier divider for all the corresponding pieces between both shapes. So let me show you an example here. Now, visually, again, I'm going to show you this visually, and then we'll show it to you number-wise. So visually, that means like if I take a picture like this and I clone it, similarity means that I take this picture. So right now, these pictures are congruent. They're exactly the same. They match up exactly. Okay? They're exactly the same. If I scale it up like this, if I take the corner and drag it like this shape is now similar to that shape because it doesn't match up exactly. So not quite exactly, obviously, but each line, each segment is the same size more than its counterpart here. Like each of these lines might be twice as long as they were originally, or 1.5 times as long as they were originally. Or if I make it smaller, each of these lines might be half as long as what they were originally, or 1/3 as long as what they were originally. That's what it means to be similar, is that there's a common multiplier for each corresponding segment. So this line is half as long as it was originally. This line right here is half as long as it was originally, that sort of thing. If I use more of a basic shape like a rectangle, same idea. So these two shapes are congruent. This shape might be twice as big as the original shape, so this length and this width, or vice versa, might be twice as big as their originals. Or if I scale it down, maybe this is like a fourth of as big as it was originally. What it's not, let me just delete this here, excuse me, let me just delete this here and get another clone. So if it's not similarity, it can still be changed. Like for example, here, if I shrink it like this, come on, there we go. If I shrink it like this is not similar to that because what happened here was, come on, I changed the left and right version of it. I don't know why it makes that distortion there, but well, I changed how long it was left and right, but I didn't change how tall it was by the same amount. So again, these might be somewhat congruent. Maybe this is like lit like that. So these might be congruent, but if I shrink it down left and right more than I shrink it top and bottom, then it's not similar or congruent because they don't hold the same scale. This is the same size as it was originally roughly, and this is a lot shorter than it was originally. So there's a mismatch there. Not everything is uniform, not everything is the same scale factor. Same would be happening if I did it like this. If I get them to be clones again, let's say like that, somewhat of a clone. If I shrink it top to bottom, these shapes are no longer similar because the width has stayed the same, the length has stayed the same, but the width has gotten drastically shorter on the second image, not the same way as the width has. So even if I did it like this, come on, these are still not similar because yes, the length and the width have both gotten smaller, but the up and down, the height, I should say, maybe I should say height rather than width. The height of the shape has shrunk a lot more, or a lot more than the length of the shape has. So because it's not an equal shrinkage on both pieces, it can't be similar. Similar means that each piece has been shrunken or enlarged the same scale, the same factor. So let's throw some numbers in here. Maybe that will help some of you out that are more numerically focused. So let's say I have a rectangle 12 by 4 or 4 by 12. I want to identify a similar shape, a congruent shape, and a neither shape. Well, pretty clearly this one right here is congruent, right? 4 by 12, 4 by 12. This is going to be congruent. Okay? What about this one here? 1 to 3 compared to 4 and 12. Well, if you want to check if they're similar, you have to think for a minute, how can I get from 4 to 1 using multiplication or division? Because scale factor is all about multiplying or dividing, enlarging or shrinking, multiplying or dividing. How can I get from 4 to 1 by multiplying or dividing? Well, I could divide by 4. 4 divided by 4 is 1. Well, how can I get from 12 to 3? Well, again, 12 divided by 4 is 3. So because the height and the length both shrank by the same amount, they both were as fourth as big as what they started with, that means that this is going to be my similar shape. So this right here is my similar shape because it's not the same dimensions, but each dimension has shrunken by the same amount in terms of multiplying or dividing. This is as fourth of as big as what it was originally. This is a fourth of as big as what it was originally. Or again, you can go backwards too. How do I get from 3 to 12? Well, I times by 4. How do I get from 1 to 4? Well, I times by 4. So your scale factor here, your SF, your scale factor, is either 1 to 4 or 4 to 1, depending on how you go. From small to big or big compared to small. So this says every 1 unit on the small shape is equal to 4 units on the big shape. Or again, you can reverse it. Every 4 units on the big shape is equal to 1 unit on the small shape. However you want to think about it. But again, if you look at the 1 to 4, it makes pretty clear sense, right? Every 1 unit on the small is 4 units on the big. Well, I have 1 unit here. That means I have 4 units here. 3 units here, so 3 ones. Here I'm going to have 3 fours. 3 ones make 3. 3 fours make 12. What about this shape over here? How do I get from 4 to 2? Well, I can divide by 2, and that gets me from 4 to 2, which means that if this shape is similar, 12 to 10 should also be dividing by 2. But it's not. 12 divided by 2 is 6, not 10. So this is my neither shape. This is neither similar nor congruent. It's smaller, but it's not small in the same proportions as it needs to be in order to be similar. This is more like 4 minus 2 and 12 minus 2, which you might think is a pattern, but in terms of similarity, that doesn't matter. Similarity is all about multiplying or dividing, because if you multiply or divide, it's, again, kind of a deeper change, almost, to kind of use non-mathy terms about it. It's a deeper change than just lopping off edge pieces there. So it's all about multiplying or dividing by the same number, not subtracting or adding. So 4 to 2, 12 to 10 doesn't match up, so it's a neither shape. Or again, you can even write that as a fraction. 4 to 2 does not match up with 12 to 10. Since those fractions are not equal, you can check them yourself if you want to, then it's a neither shape. Here, 4 to 1 is the same as 12 to 3. So because these fractions are equal, then we know it's similar. And because these fractions are exactly the same, 4 to 4, 12 to 12, that's how we know it's congruent. So similarity has a common multiplier or a common divider. Neither shapes don't. Now, for a 3D shape, it's simply the same idea, you just have more of them. So for a 3D shape, you simply have more numbers to deal with. That's it. So if I call this, let's say call this shape A, shape B, and shape C. So I want to know of these shapes which are similar, which are congruent, and which are neither. And if they are similar, what's the scale factor? So let's start with shape A here. So for shape A, I have 4, 6, 9. For the given shape, I have 8, 12, 16. Now I have to make sure I match up the correct corresponding pieces. Like for example, this 4 here goes left to right. So it should match up with other left to right pieces, like this 8 here. So I'm going to say 8 went to 4. So 8 to 4. 6 goes front to back. So 12 goes front to back here. So 6 to 12. And 16 goes top to bottom. And 9 goes top to bottom there. So actually, I should make sure I do it in the same order. Some of you might be screaming at me right now. This second one should be 12 to 6. Why is that important? Well, here I went 8 to 4. I went big to small, original to non-original. So here I went 12. I should go 12 to 6, not 6 to 12. I need to keep that consistency. Big to small, big to small. Here it's also going to be big to small. So if these three fractions are equal, it's similar. If they're not, then it's neither. So 8 to 4, well, 8 divided by 4 is just 2. So that's 2, or 2 over 1. 12 divided by 6, well, that's also 2. 16 divided by 9 definitely isn't 2. Come on. 16, 16 divided by 9 is 1.7. Close, but not quite 2. So this would be a neither shape. Because although these two pieces work, the last one doesn't. And all three of them have to have the same answer or the same reduction in order to be similar. Let's check shape B here. So again, 2 goes left to right, 3 goes front to back, 4 goes top to bottom. So 2 is going to match up with the 8. I'm going to do this backwards. I'm going to put the smaller one on top just to show you that it works both ways. So for shape B here, 2 matches with 8. 3 front and back matches with 12. So 3 matches with 12. And then 4 top to bottom matches with 16. So 4 matches with 16. So I can either reduce these fractions or make them into decimals, kind of like I did here. So 2 divided by 8, that's 0.25. 3 divided by 12 is also 0.25. And 4 divided by 16 is also 0.25. So because all these three work, this is a similar shape. This shape is similar. And in this case, the scale factor is simply either one of these three fractions reduced. So pick one of these fractions, let's say 2 over 8, and reduce it. So 2 over 8 reduces down to 1 over 4. And that is your scale factor. That is the scale factor. And specifically here, this would be the scale factor of B to given, because B is the one on top. So the scale factor of B to given is 1 to 4. If I want the scale factor of given to B, that'd be 4 to 1. So usually when they want you to write the scale factor, they will tell you what order they want it in. If they don't, then it's up to you. You get to choose. What about C here? C is going larger, but again, larger shapes can still be congruent, or sorry, can still be similar. So we'll do, again, left to right, front to back, top to bottom. So 24 is left to right, so I'll do the bigger one on top this time. So 24 to 8. 36 is front to back, so 36 over 12. And 48 is top to bottom, so 48 to 16, making sure I keep those fractions nice and consistent. So we have 24 over 8, which is 3, 36 over 12, which is 3, and 48 over 16, which is 3. So all of these here come up being 3, which means that this is also a similar shape, because every side has changed by a factor of 3. The scale factor in this case, if you want the scale factor of C to given would be 3 to 1. 3 to 1. Every 3 units on this is worth 1 unit over here, right? So C to given, big to small. If I want the scale factor of given to C, that would be 1 to 3. Every 1 unit on here is worth 3 over there. Now, how do I get these numbers here? Well, it comes from these fractions. I simply picked a fraction like 24 over 8 and reduced it. So 24 over 8 reduced is 3 to 1. So I know that that's my scale factor, and it's just a matter of putting them in the right order. So 3 to 1 means big to small. Well, the big shape is C. So C to given is 3 to 1. If I want to flip it, it'd just be the same thing. It'd just be given to C is 1 to 3. So again, they will usually tell you what order they want you to write your scale factor in when they ask. So make sure you pay attention for that statement there. But again, the only thing that's changed for 3D shapes is you have to make sure you include all the sides they give you and make sure you check out each side that has been labeled for you. If they don't label it, you obviously don't need to check it. So I don't need to check these dotted lines back here because they didn't give me numbers for them. But if they did, I would need to check them to make sure that it's consistent with everything else. So let's look at some more common shapes here. So here we want to figure out if they're similar, and if they are, what's the scale factor? And this says scale factor of A to B. So I want to make sure that my fractions have A on top and B on bottom when I make my scale factor, just to make sure that, again, I'm consistent with the way they want me to write it out. So set up our proportion. So set up our fractions. Again, the proportion is just simply a fractions that are equal. So I'll take, let's say, 6 and 4, because 6 and 4 are both the radii of the bottom circles. So 6 to 4 is equal to, because again, proportions should be equal, 18 to 12. Again, height to height. So 18 to 12. 18 to 12. So that's my proportion. Now my second step is to check if this is equal, to check if this is actually true. I can do that by either cross multiplying or reducing. So like, for example, 6 to 4, 18 to 12. The cross multiplying way means that you take the top times the bottom, top times the bottom. If these come out being the same, then they're similar. If these come out being different, then they're not. So if I take 6 times 12, that's going to be 72 is equal to, and if I take 14 times 8, or 18 times 4 rather, that's also going to be 72. So this would be similar. I'll put sim for short. These are indeed similar because my cross multiplication ends up being the same. If you have more of a fraction brain, then you can simply look at this and say 6 over 4 is equal to 18 over 12. Well, if I reduce 6 over 4, divide them both by 2, that'd be 3 over 2. 18 over 12, I can divide both of these by 6. So divide by 6, divide by 6. And it also gets me 3 over 2. So that checks out. So both of these are valid ways of checking if your numbers end up being a similar shape. So these are both similar shapes. Are these two shapes here are similar because this fraction end up being equal to this fraction. 6 over 4 does end up being equal to 18 over 12. How do I know? Well, I can check it by cross multiplying, or I can check it by reducing both fractions and seeing if their lowest terms are equal. Now, because it's similar, we need to state the scale factor. So the scale factor, in this case, they want A to B. So they want A to B. So that means I want to take my A number and put it over my B number, which in this case is what I did here. That's why at the start, I want to make sure my fractions follow this format. So when I get down to this step, I already kind of have it set up here. So 6 to 4 could be one fraction I choose here. So my scale factor would be 6 to 4. And your scale factor should always be reduced. So like I said, we're going to reduce this down to 3 to 2. So this would be my scale factor. This would be my SF, 3 to 2. For every 3 units on shape A, there are 2 units on shape B. That's what it literally means. Every 3 units on shape A is worth 2 units on shape B. Now, there's a few ways you could write the scale factor, by the way. You can write it as a fraction, 3 over 2. You could write it as a colon, so 3 to 2. Or you can write it using the word 3 to 2. So all of these mean the same thing. And these are all A to B, A to B, A to B. If they said I want the scale factor of B to A, then you would just flip these numbers. 2 to 3, 2 to 3, 2 to 3. So again, pay attention for this statement right here so you know how to set up your scale factor and you don't miss points for a silly mistake. So what about this one here? This is a pyramid shape, a rectangular pyramid. And I want to check if it's similar, and then again, if it is, what's the scale factor? Now, because I have 3 measurements labeled in each shape, I need to check all 3. And I need to make sure that I pick out the right corresponding pieces. So the first thing is to set up my proportions. I have 3 segments, so I'm going to have 3 fractions. So set up my proportions. 50 goes left to right, so that's going to match up with the 60 here. So 50 over 60. And again, I'm doing A over B because that's what they told me there. 20 goes front to back, so 24 also goes front to back, so it'd be 20 over 24. And then this 24 goes top to bottom, and this 36 goes top to bottom, so those are going to match up, 24 to 36. And again, everything is consistent, A to B, A to B, A to B. If you're not consistent, you're going to end up getting the wrong answer every time. So just to make sure I double check myself, A to B, right? A to B, right? A to B, right? And again, left to right, left to right. So left to right, front, back, front, back. So front, back, and then up, down, up, down. So up, down, up, down. So now if I want to check if they're equal, I can either divide these or reduce their fractions. So let me just go ahead and divide them because they're kind of big numbers. So 50 divided by 60, that's 0.83 repeating. So 0.883 repeating. Here, 20 over 24, 0.83 repeating, looking good so far. That's okay. If this is 0.83 repeating, we got a similar shape. So 24 to 36, so close. 0.6 repeating. So because this one didn't agree with the other two, that means this is not similar, and then that's what we'll leave our answer as. We don't have a scale factor if they're not similar, because obviously if I said what's the scale factor of this, your answer would be I have no idea, because there's two different sets of scale factors here. Similar shapes have to have a consistent scale factor between all pieces, or like here, a consistent scale factor between all three pieces. If just one of them messes up, then the entire thing doesn't work. So all it takes is one script, which is why you have to check all the pieces. If there are 4 or 5 segments, check all of them, because a very easy trick to do on tests and quizzes is to simply give you 4 pieces to check and have 3 of them work. And then that last one, the fourth one that you're going to be burnt out and not checking, that's the one that will show you that it's not similar. So make sure you check all your segments. So that's it for this video. It's just a video on checking to make sure that how to identify if shapes are similar. Next video, we'll go into how to use the fact that they're similar to solve for different pieces. Like, for example, if I said that this was x, and I said solve for x, how can we use the fact that they're similar to help us solve for x, which we've actually done a little bit in the past. So some of you might have remembered some of the stuff we did to find out what x was. But again, that's what we'll go over next time. So hopefully this helped you out. I keep clicking that, click on that. Hopefully this helped you out. Again, if you have any questions, please let me know. Otherwise, have a good day.